Hello, I'm Luz Ángela Garcia, and I'm going to talk about studying accelerated expansion with a diffusion dark energy model. I'm going to start by thanking the organizers of the Cosmology from Home for giving me the opportunity to talk, and I want to highlight that all the results that I'm going to present have been published at last year in Pirato and Garcia. Okay, so let's start by reminding us what's the concept of diffusion. So basically what we have is a solvent and a solute, and these two start to interact and exchange energy in different methods or in a phenomena that it's describing macroscopically what is happening in the small interactions. So here we have a video that shows in a very simplistic way what happens when we put in contact two fluids represented in red and blue. But we can also study different diffusion processes in chemistry and physics. And for instance, when a perfume is released from the bottle, the particles that compose this liquid start to spread out and generate some or have some interaction with the particles in the air. The GIFs that you see here are basically described in different ways that we can think about diffusion. But it's important to say that usually these processes occur inside a space. And there is a diffusion coefficient, sigma, that is going to define how the speed on how fast this process occurs. In particular, in here, when we see in the cartoon in the lower left panel, we see that the particles start very concentrated and then propagate inside this space. So we can think about the expansion of the universe as a diffusive process, but we need to take into account that this is not exactly what we were showing before, because the universe is not a fixed thing in the space-time. Is actually not confined. So we cannot actually think of something that is spreading out or in as galaxies, for instance, inside a fixed universe. So that's why we need to include this process inside the framework of the general relativity and take into account that the left side is representing the geometric side of this equation, and the right-hand side, it's actually showing the content, the matter energy content that it's interacting inside the universe. So we can actually think about diffusion as a way to explain the accelerated expansion of the universe in linear times, but we need to do it respecting the rules of the general relativity. So we can do this in two different ways, and that's the ways that I'm going to explore during this talk. The first one is by introducing a scalar field phi that is going to be included in the left-hand side, in the geometric side of the Einstein equations. And we're going to include in the stress tensor a component sigma that's going to account for the diffusion. So we need to take into account that this term is going to affect the equations that we know and the number density of particles, in this case, the galaxies that are composed of matter. I'm not going to make any distinction between dark matter and baryonic matter, are included in this N0. And of course, this energy density is going to be described also by the scale factor. Okay, so when we include all of these equations that I showed before, we have a modified version of the Friedman equations for a Hubble rate that's pretty similar to what we have in the standard model with lambda, but instead we're going to have a term phi, and the accelerated term of the scale factor, the second equation in line from top to bottom, is showing also the contribution of this term phi. The energy fractions for the matter and the scalar field phi are described in the third line. With this, if we include the equations from the conservation of energy, we have these two equations that are related, and we can see that the derivative of the energy fraction for the matter, it's actually related with the term associated to phi. Okay, so with these two equations, we're gonna solve these two differential equations, and we're gonna have a solution for a constant diffusion coefficient sigma that are gonna have a quadratic term in redshift and are gonna depend on the energy fractions today. We also have a equation of a state associated to this system, and also a fixed or constant diffusion coefficient that is given by the energy fraction of the scalar field phi today, the Hubble constant, and the number density of particles, in this case galaxies, n0 today. But more interestingly, we can think about the diffusion coefficient as being a variable in time or in redshift. And if we consider that, the differential equation has these two solutions that we see on the upper side of the slide. And you can see that they scale as a quadratic term, but they also include a dependence with the equation of a state, and this equation of a state can take in different terms. Also, the diffusion coefficient, that now it's a function of redshift, is going to have this particular way that we're seeing inside the purple box. If we do that, we can actually rule out some solutions that are not going to give us the selected term because they are gonna be positive, and we actually want to have a selected term that is going to be negative in order to have an accelerated expansion of the universe today. So basically, this shows us that the minimum value that the equation of a state can take, in this case, with a variable diffusion coefficient, it's -1/3. This is already an interesting result because we know that in order to have a diffusion and an accelerated expansion at late times, we need to ensure that omega has to be at least -1/3 or lower than that. In here, in the right-hand side, I'm showing a plot that shows the evolution of the energy fractions for the matter component in solid lines, and dashed lines, it's what corresponds to the diffusion term that in this case is represented by scalar field phi. Also, we can think about different values that sigma 0 can take in order to have these different variable diffusion coefficients. And we see that, again, in order to have something that has some evolution, we need to make sure that this value has a particular behavior that is going to be related with the equation of a state. So this is already giving us some hints on how to introduce this diffusion effect if we want to get an accelerated expansion at late times. But there is also a different way that we can think about this diffusion. In this case, we're going to think about something that is a perfect fluid in which the galaxies are interacting, and also we're going to have a different contribution from the energy tensor. In this case, we're going to introduce a perfect fluid with a barotropic equation of the state. And this is what we get for the energy tensor that now includes a term for the energy density and the pressure defined by the variable d that accounts for diffusion. And so the new equations for the new Friedman equations that we have here are represented in the bottom side of the slide. And as you can see, we have now two terms that are somehow similar to what we have if we could introduce a form of dark energy in the equations, in the Einstein equation. In this case, we're going to have, again, the continuity equation that is going to be different than zero because now we have interactive fluids. And that's why the right-hand side of the first equation have a term sigma multiplied by the number density of matter, or if you want to think about it, the galaxies that we have in the universe, plus a energy fraction that is given by the term in the right-hand side. With this, these new equations, we get the differential equations for both the energy fraction for matter and the diffusion term. And we need to solve these equations in order to get our solutions. In the first case, again, we consider that the diffusion coefficient is constant in time. And again, we recover this evolution for the energy fractions that are quadratic in redshift. Yet again, the equation of the state and the term sigma are going to be fixed by the fractions, the energy fractions of matter and the diffusion term today, and also H naught. But if we consider a case with variable diffusion coefficients, we're going to have a trend that now is going to be again multiplied by it's going to be cubic in redshift, and it's going to depend also in the equation of the state of the diffusion and the energy fraction of the diffusion. With this, we get an equation that is going to depend on redshift for the diffusion coefficient, and sigma zero is given by all these constants that you see on the right-hand side. Basically, it's important to say that this sigma zero is going to be it's going to be always positive. So in order to ensure that, we need to make sure that omega d has to be always negative because the other constants are by definition positive. Okay, with this, we study again the acceleration parameter, and we see that in this case, in order to have an accelerated expansion, omega d has to be equal or minus 1/2, and then we have the evolution for the energy fractions of matter in solid lines in this plot on the right, and the diffusion coefficient, in this case a perfect fluid, that is shown in dashed lines. Finally, we consider something that is actually not, it hasn't been explored in cosmology, but it's quite common in chemistry, and it's that the diffusion coefficient is proportional to the properties of the solvent and the concentration of the solvent. So in the way that we introduce this components, that we do the term sigma proportional to the Hubble factor. And in this case, we get quite interesting solutions, because if you notice here, we're gonna have two terms, one that is logarithmic in 1 plus z, but also we have a term that reminds us to the solutions in the standard model. So in blue, I'm highlighting the energy fractions that we can consider are proportional to the to what we get the solutions in the standard model with lambda or dark energy. And in the purple, in the magenta lines, I'm showing a term that can be considered as a perturbative term and could be quite interesting if we want to consider the perturbation sites, the perturbations in these kind of models. Finally, we show different values for the parameter sigma and the deceleration parameter. And showing here what happens if we increase the value for sigma 0 in the coefficient sigma and also the deceleration parameter. And again, we see that these values have these terms have actually something that are close to the solutions in the standard model with omega d equals to -1. Here we have an additional trend in both cases. And basically here we have what we will get for the energy fractions with different sigma 0 values. And we're increasing from top to bottom. Okay, so finally, I want to close by saying that diffusion, it's a different way to treat and explain the accelerated expansion of the universe, and depending on the way that we introduce these diffusion coefficients, we're going to have different differential equations and different solutions for the energy fractions. Thank you so much.